Thank you all for coming today. We are the Center for Climate Science and Engineering at the University of Toronto, and we host monthly guest lectures. I am Daniela Boden, the CSE manager, and today we are pleased to feature Dr. Michael Craig from the University of Michigan. Before we get started, I would like to go through the land acknowledgement. We wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in this land. As mentioned before, we are the Center for Climate Science and Engineering, established in 2019. We are a research and education center within the Civil and Mineral Engineering Department at the University of Toronto. The CSE is made up of 8 faculty members who conform the executive team and who participate together in an interdisciplinary research at the intersection of engineering and climate science. Oya American is the center director, and she focuses on structural analysis. Marianne Hatzapolo research focuses on transportation. Paul Kushner looks at climate dynamics. Graham Norvell, professor emeritus, who focuses on health and safety processes in energy and chemical engineering. Daniel Posen looks at life cycle assessment. Karen Smith focuses on atmospheric science. Marianne Tucci focuses on building science. And Sam Merkel from University of California, Merced, whose research focuses on sustainability and resilience. And then me, the CSE manager. So why we work together and what we are trying to do. So within some of the key activities going on at the CSE are education around climate science and engineering. There are 2 graduate courses that have been developed and run in UFT, on top of 8 online learning models that were developed and are available for use in Ontario higher education environments. The team also works to do research. So the faculty members are carrying out collaborative research projects at the intersection of the climate science and engineering. And finally, the team works to do outreach events, just like this one, where we invite the public or other university people to come and give a presentation about topics that we feel are aligned with the mandate and the vision we have at the center. Please stay tuned for the CSE channels to know more details for the first lecture event of 2023. So now I would like to introduce today's speaker. Dr. Craig is an assistant professor of energy systems at the School for Environment and Sustainability and the Department of Industrial and Operations Engineering at the University of Michigan. He is also the principal investigator of the Advancing Sustainable Systems Through Low-Impact Energy Technologies Lab. His research advances energy system models to address new challenges driven by decarbonization, climate adaptation, and equity objectives. Dr. Craig, welcome, and the floor is yours.
Great, thank you so much. Let me share my screen. Yes, great. Can you see this okay?
Yes.
Wonderful. All right, well, thank you so much. It's great to be here. I will be talking for about 35 minutes, and I would love to have Q&A at the end. This is some work that I've been working on for the past couple of years, as well as a few of my students, and I'm very happy to share it. I am hiring PhDs and postdoctoral fellows, so if you're interested in that, please let me know via email afterwards, or I'll be at AGU next week if anybody will be there. So today we're going to be talking about how climate change affects power systems and how we can adapt them to climate change. And I want to start with just showing you all the different pathways through which climate change can affect different parts of the power system. On the left, we've got climate change, a very simple arrow diagram showing you some of the general trends we might see under climate change, like increasing river temperatures, increasing air temperatures. And then each of these arrows going from the middle to the right-hand side is showing you many different papers that have linked, for instance, how warming air temperatures increases electricity demand, or how changes in river levels and changes in river temperatures might affect thermal power plants and hydropower plants. We have a review in 2018. There's also one that came out a year later, looking at all this different literature where some of these arrows have hundreds of papers underneath them. What I'm interested in, though, is not so much the individual arrows, but instead the total system impact of all these different impacts happening simultaneously. So this is a simple schematic, a representative diagram, and in my research that I'll show you later, we'll actually go through this more quantitatively. But on the y-axis here, we have firm capacity, basically building power plants so that we can make sure that we have enough capacity to meet peak demand. This black line on the left-hand side here is our peak demand value. And then our dashed line here is some reserve we build in, a planning reserve margin. This is very common for utilities across the world to plan for peak demand and then something just in case. And then the left-hand bar here is labeled no impacts because we're assuming climate change doesn't exist in this world. And what we've got is some firm thermal capacity in the bottom, things like coal, natural gas, nuclear, the purple, some hydropower, and then a lot of wind and a lot of solar. And as we move rightwards in this graph, what's happening is I'm adding the impacts of climate change, some illustrative impacts, to show you how, for instance, climate change can reduce the amount of capacity we get from thermal power plants, or reduce our available capacity from hydropower or wind or solar. And climate change can increase our demand. So on the right-hand side here, what happens is when I aggregate all these impacts together at the system level, we get this gap forming between how much capacity I built and how much demand I ultimately need to meet. And so this illustrative schematic is showing us what might happen if we ignore climate change when we plan power systems. If I pretend it doesn't exist, I might underinvest in my capacity, and that might result in this gap on the right-hand side. And that gap is this thing that we most want to avoid in planning power systems. Because when we don't have enough capacity to meet demand, we have rolling outages like what happened in Texas last winter, or like what happened in California 2 summers ago. So how can we understand system level adaptation needs to make sure that I'm building enough power plants and making other investments that I need to do to adapt to climate change? This is, again, a simple schematic for how we can think about planning power systems. We start on the left-hand side with some weather and hydrology data. We convert that weather and hydrology data into things like renewable energy generation time series, like wind and solar, some thermal capacity values, and some electricity demand values. We take these inputs and we throw them into the black box of a power system model, like a planning model, and out we get investments, costs, emissions, and reliability. So this is how we've been working in the power system research and in the power system practitioner space for decades, is taking these inputs, passing them through a model. So one way that we can incorporate climate change into this workflow is by adding climate change onto the left-hand side, updating our weather and hydrology assumptions. When we update those, we can translate them to changes in supply and demand, and then pass them into our power system model. So now, instead of running on historic data, we can run our power system model, our investment model, on future weather and future climate data. And with that, then we might get an updated sense for what types of investments I need to make in my power system. This sort of framework is what I'm going to first start with in our 2 papers. These are 2 papers from last year and 2 years ago in environmental science and technology. And here what we're really trying to do is to take climate data and inform what kind of investments we need to make in the power system to avoid system level outages and other bad consequences. So this paper makes 3 contributions. First of all, we want to use a consistent framework to capture how climate change can affect different assets within the power system. Those assets include thermal power plants, like our natural gas and coal plants, our hydropower facilities, and electricity demand. We're going to look simultaneously at mitigation and adaptation. We're not just adapting to climate change without other changes happening in the power system. We're making decarbonization or mitigation decisions as we are also going to be making adaptation decisions. So we want to look at both of them together rather than focus on just one or the other like prior work does. And we're going to look at trade-offs that decision makers in the real world face between planning and operational decisions. So our research question in this paper is what trade-offs exist between power system planning and operations given our mitigation and our adaptation needs. So we're going to use the Southeast United States as our study system. This is a thermal and hydropower dominated system. You can see there are lots of rivers shown in blue on this figure, And along those rivers, we have lots of hydropower facilities, as well as large thermal facilities, things like coal and natural gas. All of these facilities, coal, natural gas, hydropower, are all vulnerable to climate change through different mechanisms, which we'll see shortly. And this system is a very large system, 172 gigawatts. It's roughly a third natural gas, a third coal, and a third nuclear plus hydropower. This data is from roughly 2018. You don't even see wind and solar in here because there's so little renewables. Those renewables have grown over time, but still they make a very small part of that system even today. So our framework for doing this is we're going to take climate data and ultimately try to get it into our power system model so that we can run the power system model with that climate data in mind to see how our investment decisions might change. We're going to start at the bottom of this flow diagram with that climate model square. And here we're going to work with climate scientists and hydrologists at the University of Washington to get downscale data from 20 different global climate models. And that downscale data includes different meteorological variables, things like air temperature and precipitation. We're going to take that future meteorological data and we're going to run it through a stream flow and water temperature model. This is VIC and RBM, both models available from the University of Washington. But this step gives us those river temperatures and river flows, which will in turn tell us how our thermal power plants and our hydropower plants are affected by future climate change. We're also going to take air temperature and link it to electricity demand through a piecewise linear regression. And so now we have this intermediate step where we've got how are our future assets impacted by climate change. And the next phase is to pass that all up into our system level planning model. And so we're going to feed those thermal deratings, the hydropower generation potential and demand into our capacity expansion model and into our unit commitment and economic dispatch models. So our capacity expansion model, this is a long-term optimization-based planning model, the same type of model that utilities in the real world use to plan their power systems. So out from the capacity expansion model, we get investments. And the unit commitment and economic dispatch model is an operational model. It tells us hour to hour for a year, here is how our different power plants are operating, and here is how we can meet demand with supply. So we've got this framework, and in particular here, it's the capacity expansion and the unit commitment and economic dispatch models that are doing this power system level operations. We want to understand trade-offs between our planning and our operational decisions. And so we're going to take the capacity expansion and the unit commitment model and run them through this experimental design. First, we're going to set a carbon policy, say a 90% reduction in CO2 emissions. This is how we capture mitigation. We're going to pass that into the capacity expansion model, and we'll run it twice. We will run it first with these impacts of climate change using RCP 4.5, and we're going to run it a second time, ignoring climate change using historic weather data. And so from this, we get out two fleets. That first fleet is informed by climate change. The second fleet is ignoring climate change. So let's look at what these two fleets look like first. So here we have these two fleets. The left-hand side is ignoring climate change. The right-hand side is planning for climate change. The middle number here is showing us the total installed capacity in our system. The left-hand side, when we ignore climate change, we only build 150 gigawatts by 2050. When I plan for climate change, though, I end up building roughly 50 gigawatts more or 30% more capacity to get to 202 gigawatts. So one impact of climate change on our investments is we just build a lot more capacity. We can also look at what types of investments are we making, and that's shown in this circle around that middle number. So if we ignore climate change, roughly 50% of our fleet by mid-century is natural gas. We've also got wind and solar significantly growing in the system, and we've still got some hydropower and nuclear left in the system. On the right-hand side, when we plan for climate change, we see that there's a large shift towards investing more in solar power. We've got less wind as a percent of the fleet, and that solar also is coming at the expense of our natural gas investments. So there's two reasons why we're building more capacity. Number one, our demand is increasing, so that's driving more investments. Number two, we're building more solar power, and because that solar power has a lower capacity factor, we need to offset those investments by building more capacity. So we've got these future fleets. Now we want to understand how do we operate those two systems, and do we have any trade-offs that we're facing between making investment decisions and making operational decisions? So we're going to take those two fleets and repeat the same experimental design with and without climate impacts, except this time we're running an operational model. So we can see this fleet we planned for climate change, we're going to send it into our operational model, and we'll run that operational model, either accounting for the impacts of climate change or not accounting for the impacts of climate change. And similarly, we'll take that other fleet that we built, ignoring the effects of climate change, and we're going to operate it with the effects of climate change and without the effects of climate change. So from this output, we get 4 sets of operational results that show us costs, emissions, and reliability. And these 4 different operational results mix and match. Did I account for climate change in my planning phase? Yes or no? And then did climate change actually affect my operations in the future? Yes or no? And so by comparing results here, we can see these trade-offs manifesting quite clearly. So let's look at those operational results. We're going to start on the left-hand side of this figure here. We've got the title there says, ignore climate change and no climate change effects. This is for the investment, the future fleet that we planned ignoring climate change. And we're going to run it through our operational model, again, ignoring climate change impacts. On the y-axis, we have electricity generation, and we've grouped it by different seasons, fall, winter, spring, and summer. And you can see the colors here correspond to different fuel types in our system. So in fall, in winter, and spring and summer, we don't see any green in any of these bar plots. Green means loss of load. That means rolling outages, the thing we want to avoid. And so we're not seeing green, which is good. And we see that a lot of our generation is coming from natural gas. I can add one more box here, which is planned for climate change and have climate change affect our operations. So this is that future fleet again that we built with climate change in mind. And then we're going to operate it with those future impacts of climate change. And again, we do not see any green. Green is the rolling outage. Green is the thing we want to avoid. Again, demonstrating that if I plan for climate change, I can take those operational impacts in the future. I'm going to add the last 2, which is our mix and match scenarios. And I'm going to focus on the right panel in this graph, which is I ignored climate change in my planning decisions, but climate change affected my operations. And here is where we really see that green manifesting, a significant amount of loss of load happening in our system. And that's particularly happening in the summer season. So here is the only system where we see this trade-off. If I ignore climate change in my planning decisions, but it affects my operations, I'm at risk of having outages. Otherwise, I am fine. I will not have reliability threats in the future. Of course, building more generators increases costs. And so we also wanted to understand if I'm investing more because of climate change, am I increasing costs and possibly passing on those costs to ratepayers? So we've got the same panels here. I've highlighted the right-hand side. In each of these panels, the rightmost graph, the rightmost bar is our total cost. So you can just focus on that total cost bar. And you can see the only total cost that's much greater than all the others is the furthest right that I've got in this red box here. And this red panel, again, is when I'm ignoring climate change in my planning decisions, but climate change is affecting my operations. And so here we see this huge increase in cost relative to these other scenarios, because I have all of this loss load, and the loss load is really driving costs. It's having monetary costs on ratepayers. It's having non-monetary costs on them. And so the only scenario where I have a significant increase in costs is that rightmost scenario. We can look at this second to the left panel, plan for climate change and climate change effects. So here we built a lot more capacity. We increased our total investments by roughly 1/3. We generated a lot more electricity. And yet the total costs on a normalized basis are not much more than in the scenario where we ignore climate change and it doesn't even affect our operations. So here we can see, while costs are going to increase from those increased investments in operations, the cost increase is not that large and is much less than the risk you face if you ignore climate change in your planning. One of the values of the study is we wanted to look at adaptation and mitigation simultaneously, which other studies had not done at the time. And so here I've got 2 more sets of results, one with a 50% carbon emission target by 2050, another with an 80% carbon emission target by 2050. And I'm just showing you the aggregate loss of load across the entire year for the 4 different scenarios we've been talking about, which are on the x-axis. And we can see in a 50% CO2 reduction scenario, we still see an immense amount of loss load. We still see a very high cost of energy if we ignore climate change. But in the 80% CO2 reduction target, we've got this interesting phenomenon where we actually don't see much green, we don't see much load, we don't see much cost of that loss of load. And this is even happening when I ignore climate change in my planning and climate change affects my operations. And so this is showing us some synergy actually, or some co-benefits between mitigation and adaptation. When I mitigate climate change, I build a lot of wind and solar, I move away from some of those more vulnerable assets to climate change, like my natural gas units. And because I move away from them, even if I'm ignoring climate change and planning, I still can avoid a lot of the impacts of climate change in that future system. So in this first paper that I've just shown you, what we did is we took our power system model, a very common type of model used in the real world and in research settings, and we updated the inputs to account for future climate change. And we found that there are very large system level consequences of our mitigation and adaptation decisions. And in particular, ignoring climate change can lead to very bad outcomes in the future. But a lot of my research is also trying to move beyond what I would call a conventional approach to trying to adapt power systems to climate change. And we want to overcome several of the key limitations of this approach. And while I say conventional, it is not easy by any means. This project that I just presented went for multiple years and involved a collaboration with the University of Washington. We went through many, many different iterations, but it's really taking how we plan power systems right now and how we think about our climate data needs, and just tries to hold everything as static as possible and just tries to update some of the inputs to this process. That has some shortcomings though. One of them is the deep uncertainty that climate change poses to us. In particular, the deep uncertainty that we have in terms of localized impacts of future climate change. So if we have this deep uncertainty, we might need to rethink how we even approach power system planning to begin with, maybe ripping out this black box and putting in some other type of methods framework. We also have a lot of challenges in creating downscaled climate data that is actually usable in the power system world. And so here we can think about different ways to think about risk to power systems to try to guide future downscaling activities in a more productive manner. And third, we might have distributional consequences. What I just showed you, we have a single cost of loss of load, but 1 unit of megawatt hours dropping or one rolling outage is not the same as another rolling outage, and it's not going to affect individuals in a certain region the same. In particular, for instance, low-income individuals who live in homes with less insulation could be at much more risk of health impacts if you have outages during extreme heat events, for instance. And so these are 3 limitations that we're trying to work on in the lab to try to better understand our adaptation needs and how we approach adaptation decisions in current systems. For the rest of the time, though, I want to talk just about the second one to show you one more bit of research that we've been working on, and that is trying to grapple with the challenges we have at downscaling climate data. I think many of you probably work on climate data, climate models, producing this data for you end users. And so I think this is could be a great discussion afterwards in terms of what you think about this and how uptake might work in your field. So the challenge here, downscaling is very hard. It takes a lot of computational resources. It takes a lot of storage resources. How can we better guide downscaling for use by power system modelers? So one way could be, can we figure out certain periods of time, certain large-scale weather conditions that are really driving most of the concerns we have in the power system? And if we can identify several critical periods or several critical types of weather patterns, we can focus our downscaling patterns in those particular periods of time rather than downscaling 100 years of 100 different ensemble members. And so to better understand this, we're going to try to diagnose what are the meteorological drivers of failures in power systems, in particular of power system resource adequacy. So this little schematic shows you generally what resource adequacy is all about. In the power system, we're always trying to balance supply and demand. Our resource adequate system has this balance between supply and demand at all times. But when demand exceeds supply, that's when we have rolling outages or blackouts, very bad outcomes. And so that is a resource inadequate system. Meteorology, weather, air temperatures, wind speed, solar radiance affects both supply and demand. And so resource adequacy is really a function of meteorology and the investment decisions we make in the power system. So we can layer on some new complications in terms of thinking about how meteorology affects resource adequacy. First of all, supply of electricity is increasingly provided by renewables. As we bring more renewables onto the system, this relationship between meteorology and supply changes. We are electrifying end uses, electrifying home heating, electrifying vehicles, electrifying industry. That electrification might moderate the relationship between meteorology and electricity demand. And finally, of course, climate change is affecting weather. As weather changes, it will change supply and demand. All of that in turn is going to affect resource adequacy. So there's one literature that we're working with here, the resource adequacy literature. And so this literature is really asking, as I build more renewables or as I electrify demand, how does that change resource adequacy? This literature is not dealing with meteorological drivers of failures in resource adequacy. There's another literature that is looking just at the meteorological drivers. As climate change is affecting weather, how is weather affecting wind supply and demand, for instance? But this literature, which mostly is done in Europe actually, isn't actually quantifying this key concept of resource adequacy in power systems. And this concept of resource adequacy is something that utilities are dealing with on a day-to-day and a year-to-year basis. And so our research is going to try to connect these literatures. We want to link meteorology to resource adequacy explicitly in our analysis. And we're also going to look at how increasing renewables might change the relationship between weather and resource adequacy. So we have two research questions in this paper. Number one, what large-scale weather patterns drive power system reliability? Reliability is a synonym with resource adequacy for the purposes of this presentation. And number two, how does this relationship change with increasing renewables penetration? We're going to start with three different inputs. I'm going to build out the high-level method structure for this paper. We're going to start with current generators, current electricity demand, and weather patterns. We're going to run our study over WEC. This is the Western U.S. This is all one interconnection in the Western United States. And you can see in this map, stars, triangles, showing you where solar plants are today in WEC, where wind plants are, and where natural gas is. And you can see solar and natural gas really concentrated towards California and Arizona, where we have most population living. Wind is more evenly distributed. So we're going to take this existing generator fleet, we're going to take demand, we're going to take different weather patterns, and we're going to run it through a capacity expansion model or a long-term planning model. Similar type of model we saw in the last research paper. It is going to tell us, here are the investments that you would make, here is a future generator fleet, in order to comply with certain renewable energy targets. So if I want to study a 40% renewable energy system, I can use the renewable energy target to force the capacity expansion model to build those renewables. So from this, I have a future generator fleet, and I can modify again how many renewables I put in there to look at the relationship as it changes as I increase renewables. I'm going to take this future generator fleet and I'm going to run it through a resource adequacy model. This is a Monte Carlo based simulation model. And what it's going to tell us is, when does our system reliability fail? When do we have loss of load or outages or blackouts? In particular, we're going to quantify this as the hourly loss of load probability. In this hourly LLP, this is a common metric that you see utilities using in the real world. We have standards set according to LLPs. And so one of the values of this paper is that utilities deal with these sorts of quantitative measures all the time for understanding power system reliability. We're going to come back to the weather patterns, and what we want to understand is how meteorology is driving failures in system reliability. And so to understand that link between weather and reliability failures, we're going to use a method from the meteorological domain, which is a self-organizing map. This is an artificial neural network-based technique that does some clustering of patterns across space. We'll see that shortly. And finally, once I have these weather patterns established, once I have when my failures happen, I can draw a link between the two and understand which weather patterns drive low reliability events or failures in reliability. So we're going to see the self-organizing maps in a couple slides that will make more sense to you. I want to start with showing you what our future generator fleets look like, and then what their hourly loss of load probabilities or what their hourly system reliability looks like first. So here we have on the x-axis 3 different systems that we'll be looking at for this study. The current system, a 20% renewable system, and a 40% renewable system. This is all coming out of our capacity expansion model. On the y-axis, we have installed capacity, and we've got 3 different lines for natural gas, wind, and solar. we're going to simplify our analysis and only focus on these 3 generator types for now. So you can see in the current system, we've got roughly 20 and 30 gigawatts of solar and wind and about 110 gigawatts of natural gas. As I increase my renewables penetrations, I build a lot more wind and solar, and the installed capacity of my natural gas declines in turn. So in this 40% renewable system, we've got about 70 gigawatts of solar, 80 gigawatts of wind, and 80 gigawatts of natural gas. So lots of renewables. When are these systems at risk of failing? So we can look at these hourly loss of load probabilities, which again is showing us when might these systems be failing. The top left box here on the y-axis is our hourly loss of load probability. So a value of 0.1 here means in that hour, there's a 10% chance of my supply not being able to meet demand. In other words, there's a 10% chance of a small outage occurring in my system. On the x-axis, we've got the year 2019. And so you can see that there's a cluster of spikes around the summer months. So one important takeaway is in the current system, all of the risk to the system in terms of failures is happening in the summer months. And there's no hour that's really dominating the risk. There's lots of hours with some small amounts of potential unserved demand. The bottom figure is showing us when are these risks happening. Here we're just looking at those summer months. So we've zoomed in on when those blue lines are occurring. We're May to October on the y-axis, or September rather. And then on the x-axis, we have hour of day. And so here we can see most of these threats to reliability are happening around 12 to 8 p.m. local time. So really in the early evening is when we have solar power falling off, we've got demand increasing, and this is when we see a lot of threats to system reliability. We can look to see if anything really changes when I increase the installed renewable capacity from 13% in the current system to 40% in this future system. And so in general, there's not much changing. We still have this concentration of risk in the summer months. You can see that concentration of blue bars is in those summer months. And in the bottom figure, one thing that we do see is that the risk is typically moving later on into the day, more into the early and late evening. And this is because as we build more and more solar, we've got lots of generation during the sunny day hours. We've got less generation available in the evening hours, and that's when our risk is manifesting more so in this system. So we've got one piece of the puzzle that we want to understand. When are outages occurring? But we don't just care when they're occurring, we want to understand what weather is driving those outages. And so now we're going to look at those weather patterns that I talked about before. So here we've got a map, 12 different maps. They're labeled WP 1 through 12. That means weather pattern 1, weather pattern 2, all the way down to weather pattern 12. And this is the output of our self-organizing maps, that meteorology technique that I mentioned earlier. So what this is doing is this is taking high-level pressure anomalies, the Z500 daily anomalies, and it's clustering them into 12 different large-scale weather patterns. You can see in the bottom left, this large-scale weather pattern features a high-pressure anomaly over the Pacific Northwest. In the top right, we've got a very low-pressure anomaly over the Pacific Northwest. And then as I move from top right to lower left, you see a slow transition in those weather patterns. You see, as you move leftwards, for instance, increasing pressure over the central northern United States. And so the value of this SOM is that it's showing us these large-scale weather patterns and showing us that there are 12 distinct weather patterns in this area. And we also ran this with different numbers of weather patterns. Our results are robust, whether you assume 9 or 12 or any other number. And we selected 12 based on goodness of fit of the SOM. So we've got these weather patterns. We've got when our reliability failures occur. Now we want to understand in which of these weather patterns do those reliability failures happen? Are all the reliability failures that I observe happening in weather pattern 4, or all they are, for instance, happening in weather pattern 9? So this figure is showing you different squares for the different weather patterns, except instead of looking at the weather, I'm looking at the number of risk hours that belong to the weather pattern. So in the bottom left, for instance, this bottom left square is weather pattern 9. You see 3 different values for the current fleet, the 20% renewable fleet, and the 40% renewable fleet. And the y-axis is showing us that in the current system, for instance, we've got 80 hours with a loss of load probability greater than 0. In other words, 80 hours where there's some chance of an outage actually happening. And all of those 80 hours occur when weather pattern 9 is in effect in our system. Weather pattern 10, 7, 8 also are adding some risk to our system. We see some risk hours happening in weather pattern 8, in weather pattern 7, and in weather pattern 10. But in those other weather patterns, 1, 2, 3, 4, 6, 5, 11, 12, we see no risk happening, or a tiny bit in one, in the rest of them, no risk happening. And so this is showing us that weather pattern 9, in terms of the number of hours at which we're at risk, is really driving things, as are 8 and 10. And so these are the high pressure anomalies that I showed you on the last figure. Weather pattern 9 is the highest pressure anomaly over the Pacific Northwest. 8, 7, and 10, though, all feature some different versions of a high pressure anomaly as well. Why are these high pressure anomalies driving reliability risk in our system? Well, we can look at the different weather impacts of those anomalies on the surface. In other words, those weather conditions that are affecting the power system. First, we can start with surface temperatures. Surface temperatures, as they increase electricity demand because people need more electricity for air conditioning. They negatively affect our solar panels because they become less efficient. They reduce the efficiency of our thermal power plants. So high surface temperatures have bad consequences for the power system. Weather pattern 9 in the bottom left is where we saw risk mostly happening. And we see weather pattern 9 has a positive surface temperature anomaly, meaning the high pressure event is associated with increased surface air temperatures. 8, 10, 7 also have elevated surface temperatures. And so this makes sense why these weather patterns are driving reliability failures. We can look at solar radiation anomalies. This solar radiation tells us how much power we get from our solar panels. In general, there's not a clear message here. In weather pattern 9, we see a small downward anomaly in solar radiation, especially where we have our solar panels, indicating we're getting a little less solar generation. But in 7, 8, 10, not really. Where we see a clearer trend, though, is in our wind speeds, which are going to drive our wind generation. And in weather pattern 9, we see a downwards anomaly in our wind speeds. And so as this high pressure event is occurring, we have higher temperatures, which is stressing the system, and we have less wind and a little less solar, further stressing the system. Our finding that high pressure anomalies drive the risk of outages is robust across our studied weather years. Everything that I showed you before was for a single weather year, 2019. We ran our analysis on as many weather years as we had enough data for, which is 4. Here on the x-axis, we have our different renewable penetration systems. The blue lines are weather pattern 9. The y-axis is number of risk hours. And so the important thing here is the blue weather pattern 9 is more important than the other colors, indicating that weather pattern is more important than the others. We can also look not just at number of risk hours, but instead the total risk, the cumulative loss of load probability. And here we see weather pattern 9 dominating even more. Across all 4 weather years, across all of these renewable penetration systems, we see weather pattern 9, that high pressure anomaly, really driving most of the threats to system reliability. So we ran this analysis. These are, I think, interesting results. We really enjoyed the paper, but one thing we asked was, well, we had this nice natural experiment, unfortunately, because California ISO in 2020 had rolling blackouts. And so we should be able to go back into the record for 2020 and look at the weather pattern and see, is the weather pattern that existed during those rolling blackouts what we would have thought based on our research? And we find that, in fact, it is. These are the 2 days where California had those rolling blackouts, August 14th and 15th, 2020. And you can see what we're showing you here is at high pressure, or is the Z500 daily anomaly. And you can see that it looks just like our weather pattern 9, a high pressure anomaly over the Pacific Northwest. And in fact, if we take these anomalies and run them through our SOM, it categorizes them or clusters them as weather pattern 9. So this is a nice validation of our results and our insights. These are really some of the main drivers of reliability threats in the Western United States. This means that if I'm thinking about generating downscaled climate data for power system modelers to understand reliability threats under a future climate, I could start with just looking at daily Z500 values from different climate models. Select those that belong to this weather pattern or show this high pressure anomaly and start just by downscaling those. And I could also think about developing new downscaling methods that perform better for these types of high pressure events than for other types of large scale weather patterns. High surface temperature anomalies that we see associated with these patterns could have very inequitable impacts during outages. This is something we're working on right now. But if you have increasing extreme heat, if you have outages that are occurring during that extreme heat, it's probably low-income populations or more urban populations where you have the urban heat island effect in force that are going to suffer more during those outages. And vulnerability to these patterns is not destiny. We can change this through different mitigation decisions, market rules, and adaptation investments. And this is another area that we're trying to investigate further. So I am 1 minute past time, but that's all I have for today. This work was funded by the National Science Foundation. And thanks so much for being here. Thanks for your time and attention. And I'd be more than happy to answer any questions you have.